I'm Dr. J, and this is a video about confidence intervals. This video exists in a playlist all about statistical inference, covering both Bayesian and non-Bayesian approaches to inference. There's also a PDF version of these slides in case you wanted to print them out. In this video, we'll talk about both exact and approximate confidence intervals. We'll talk about them in the context of normal and binomial models. All right, so let's start out with the definition. So the coverage of an interval estimator is the probability that the interval will contain the true value of the parameter when the data are considered random. So we're thinking about collecting a number of different intervals, right, as we collect different samples of data, and saying how often do those intervals contain the truth. And that's called the coverage. If an interval estimator has a particular coverage, say a 95% interval, then we call it a 95% confidence interval, and 1 minus a is the confidence level. So 95% confidence intervals have a 0.95 confidence level. So basically what we're doing here is we're doing this probability calculation, right? So the probability that we have this lower endpoint and upper endpoint on that interval, the probability that those contain the true value, theta, we want to make sure that that's at least 1 minus a. But the key in this expression here is to recognize that what's random for this discussion is the L and the U. Right? That is, the endpoints of the interval are random because we are collecting different data sets. And we're saying how often do those different data sets, when we construct an interval, how often does that interval contain the truth? The key thing to recognize is that confidence is really a statement about the procedure that's being used, and not a statement about a particular data set or a particular parameter that's of interest, but instead it's a statement about that procedure of how you're constructing confidence intervals. All right, so let's talk about a normal model. Right, so here we have a collection of independent, normally distributed data with a common mean mu and a common variance sigma squared. And we're going to provide or calculate our Bayesian credible interval using our default prior of 1 over sigma squared. And we know that the formula to calculate that Bayesian credible interval, or we should know that formula. If you don't know that formula, you might want to go and check out the video up here talking about where this formula comes from. So the formula that we have is that we take the sample average, we do plus and minus, or we add and subtract this t critical value, we multiply by the sample standard deviation and divide by the square root of the sample size. And when we do that, we have an appropriate credible interval. That credible interval will depend on the exact t critical value that we'll use, which will depend on a, the amount of error that we're allowing ourselves. For example, if we want a 95% credible interval, then a is 0.05. Now, if we think about the data as being random, then we can calculate this quantity right here, the sample average minus the true mean divided by the sample standard deviation over the square root of the sample size. And you should know right away what distribution this quantity has. If you don't, there's a hint up here and a suggestion that maybe you go watch that video, because the solution here is that it's a standard t distribution with n minus 1 degrees of freedom. All right, so now we can ask the question, well, what's the probability that this procedure, that is, if we calculate these two endpoints using the formula up here, if we calculate that for a whole bunch of data sets, what's the probability that that interval will actually contain our true mean, mu, of our normal distribution? And it's good in this case because we can actually do that calculation. So we can just set up, here's our left endpoint, here's our right endpoint. What's the probability that those two, because they're random, will contain our true parameter mu? Now we just do some rearrangement. So we rearrange so that we calculate this t statistic right here, the sample average minus that mean divided by the sample standard deviation over the square root of n. Now the quantity in the middle between those two inequalities, we know what distribution that has because we put right up here, right? That is a standard t. So we're going to denote that with t n minus 1, or a capital T n minus 1. So now the question is, what's the probability that that capital T is between these two lowercase critical values? And it turns out that they're chosen precisely because they give the appropriate probability of 1 minus a. Right, so what does this tell us? This tells us that our Bayesian credible interval here is also a confidence interval. That is, the procedure that we are using has the appropriate coverage. So when we say it's a 95% confidence interval, that means that 95% of our intervals using this procedure will cover the true value. All right, so let's take a data example here. In a previous video, the I04, there'll be a link up here, we talked about a random sample of farms in Iowa, 9 of those, and they had an average yield of 186, and a sample standard deviation of 22. And so we're going to use those sufficient statistics to calculate the credible interval for the mean yield across Iowa. So we found that credible interval to be 169 to 202. Because it's a credible interval, that tells us that our belief about what the true population mean is 95%, that is between 169 and 202. Because that credible interval also corresponds to a confidence interval, that tells us that the procedure we're using, that is, if we did this over and over and over with different samples of farms in Iowa, that 95% of those intervals would cover the truth. A little bit of an issue here is that confidence interval, knowing that it's a confidence interval, actually doesn't tell us anything about this particular data set that we have. Right? It doesn't tell us anything about whether or not the true value is in that, or whether we should believe that the true value is in that interval. Right? We get that interpretation because it is a credible interval. Okay, so we're going to move on now. That was the one example where we could talk about exact confidence intervals. And we're going to move on to be talking about approximate confidence intervals. And to talk about approximate confidence intervals, it's going to be convenient to remind ourselves what the standard error of an estimator is. So there's a video up here where we previously talked about the standard error of an estimator, but we're actually going to change the definition slightly. So the way we're going to change the definition is that we're going to make the standard error an estimate of the standard deviation of the estimator. Previously, our definition just said it was the standard deviation of the estimator, but an issue will arise where we don't always know what the value is for population parameters that are needed to calculate the true standard deviation of the estimator. And so instead, we're going to use an estimate of that standard deviation. And one of the key criteria is going to be that estimate is consistent. All right, so let's look at a couple of examples of what the estimates that we're talking about. So here's the first example. Suppose we have binomial data with a number of trials n and a probability of success theta, and we're interested in estimating theta. We'll usually do that through the sample proportion, that is y, the number of successes, divided by n, the number of trials. And we can calculate the standard error here, and that standard error is going to be the square root of theta times 1 minus theta divided by n. And now with our previous definition, we will be plugging in theta here and not theta hat, right? That is, we'd be plugging in the true value for theta. Of course, the whole reason we're doing or collecting the data is because we don't know what theta is. And so instead of plugging in theta, we're going to plug in our best guess for theta. That is theta hat, this y over n. We're going to plug that in, and that's going to be our standard error. In the second example, let's talk about normal distribution and trying to estimate the normal mean with the sample average. Okay, we can calculate the standard deviation of that sample average, right? And we would find that it's sigma divided by the square root of n, where sigma is the population standard deviation, but again, we don't know what that is. And so instead of plugging in sigma, we're going to plug in an estimate of it, and we're going to use here the sample standard deviation. That's just the square root of the sample variance. And so if we plug that in, then our standard error for the estimator for the mean, the sample average, is the sample standard deviation divided by the square root of the sample size. Okay, so we're going to use the standard error to construct approximate confidence intervals. And so we're going to be focusing on primarily unbiased estimators, and those unbiased estimators that have asymptotic normal distributions. If you hear that phrase, asymptotic normal distribution, you should be thinking to yourself, Central Limit Theorem. If you're not thinking Central Limit Theorem to yourself, you might want to go back and check out the Central Limit Theorem video. Right? So we know that means and averages of IID random variables have an asymptotic normal distribution. And so when the estimator is the mean or sum of IID random variables, then we will be able to use this formula. And most commonly we do so when we're talking about the sample average. The way that we construct the approximate confidence interval is for a particular parameter theta, is that we take an estimator of theta, in particular an unbiased estimator of theta, and then we add and subtract this z critical value times the standard error of that estimator. Okay? And this z critical value is found by just saying, well, that's the value such that probably that a standard normal random variable is greater than it is in fact the correct probability, a over 2. All right, so this formula says, look, find the estimator, find its standard error, and then compute the approximate confidence interval by taking the estimate plus or minus an appropriate z critical value times the standard error. Now let's talk about why this is actually true. That is why this formula will construct an approximate confidence interval. And we'll start out with the fact that we have an estimator that is an asymptotic normal distribution and it's unbiased. That means it's approximately normal. The mean is that expectation, which is unbiased, which means that's the parameter we're interested in. And the variance is that standard error squared. And now we'll do the same kind of calculation we did with the normal model with the credible interval, but instead of using a t-distribution, we'll be using normals. And so we start with the formula of the probability for our left endpoint being less than the parameter of interest, which is less than the right endpoint of our interval, and ask, what's that probability when the data or these endpoints are considered random? We're now going to rearrange by subtracting off the estimator and subtracting or dividing by the standard error. And so we get a formula that looks like this. By symmetry in the normal distribution, right, the negative of z, right, all right, so we can do some rearrangement and we can find this particular statement. Now, the quantity between the two inequalities is going to be a standard normal because we're taking a random variable, subtracting off its mean, and divided by its standard error. And because that random variable is normal, we now have a standard normal, and so that is z. And now these z critical values were particularly chosen to have the right probability, and so it turns out that this probability is going to be 1 minus a. All right, so let's go back to our normal example and think about having an estimator that's our sample mean. We can calculate its standard error that we showed earlier. Now we can construct an approximate confidence interval using these quantities. So we have a formula for the approximate confidence interval for a normal mean. That is the sample average plus or minus a z critical value times the standard error, which is the sample standard deviation divided by the square root of n. And now this interval looks very much like our exact interval we talked about before. Here's the exact interval, and the only difference between the two is that we have a t critical value in our exact interval, and we have a z critical value in our approximate interval. And it turns out that when the sample size is large, that is when the degrees of freedom on that t-distribution are large, then the z critical value and the t critical value are almost exactly the same. And so here's a plot that kind of demonstrates that point. So this plot has z critical value on the x-axis, the t critical value on the y-axis, and it has a gray line that's the y equals x line. That's the places where the z critical value would be equal to the t critical value. Now we can see in that red line that's very far from that 45-degree line that we are very far away. That is, the z critical value and t critical value are not very similar when our sample size n is small. But as that sample size n increases, that line keeps moving closer and closer to the 45-degree line. That is, the z critical values look very similar to the t critical values. And so that's why this is an approximate interval, but the approximation here gets better and better as the sample size gets large. Which, after all, is what our central limit theorem tells us, and it's how we constructed our approximate normal distributions. All right, so let's talk about the binomial model. Right, so we can use the same idea for a binomial model. Our estimator is the binomial proportion y over n. That's for theta hat. and then we can find the standard error, which we did a couple slides ago. So we take the estimator plus or minus the z critical value times that standard error, and now we have a formula for that approximate confidence interval for a binomial proportion. Right? And this works because the expected value here is unbiased for the parameter, and because the standard error as we calculated before. Now we can use this formula on an example. So here's an example from a Gallup poll that interviewed 1,500 individuals in the US, presumably randomly selected, and 32.1% of those individuals said that they were engaged at work. And so we can use that information. So our estimator is 0.321. That allows us to calculate both the estimate as well as the standard error of that estimate. And we can do that and find that this is the formula we'll be calculating. Our z critical value here for a 95% interval is 1.96. And we can then do the calculation and find that the interval is the approximate 95% confidence interval. In this example is 0.34. But now I want to remind you that a confidence interval says something about the procedure that was used to generate the interval, right? So what it tells us is that 95% of the intervals constructed would contain the true value. So we still don't know whether the true value is in this particular interval or not, right? What we know is that on average, 95% of the intervals constructed in this way will. And so another way to say that in this example is to say, look, if we did another poll, and another poll, another poll, another poll, another poll, and we did that routinely, right, we would know that 95% of those intervals would cover the truth. Okay, so it says nothing about the true value for this particular interval. In summary, we did a bunch of examples of constructing confidence intervals. So the first example we had was an exact example for a normal mean. Then we did an approximate example with the normal mean, and we pointed out that the only difference between these two is a t critical value compared to a z critical value. We found an approximate confidence interval for the binomial proportion. I just wanted to extend this one further. I didn't talk about it in the slides here and in the video, but you can also do the similar thing for a set of independent Bernoulli random variables with that common probability of success. Right? So now, because the Bernoulli is just zeros and ones, the average is the estimator of that population proportion. And once you have that, then the formula looks identical to the formula for the binomial model. So the only difference between the two is that the binomial is the sum, whereas the Bernoulli is zeros and ones. All right, now previously we've talked about a number of ways of constructing credible intervals, and it turns out that the ways that we've constructed them in our default ways with our default priors, that those credible intervals also provide approximate confidence intervals. And what do we mean by approximate here? That's the other thing to keep in mind. What we mean by approximate is that the coverage of those intervals will get closer and closer to our desired coverage as the sample size gets larger. All right, so this concludes the discussion about confidence intervals. Now we are going to go and start talking about hypothesis testing and model comparison. Hope to get you there.